Hi all. In this section, we are going to give the relevance and importance of the expansion coefficient Cn, which is seen in the general expansion of the total state of the system, and we'll also discuss how we can find this Cn in case of a problem. Okay. So in general, this psi of xt, the state of the system, can be expanded in the energy eigenfunction of the form sum over n, Cn psi n of x e raised to minus ent by h cross. So recall this psi n represents the stationary states, or it is also called the energy eigenstate, corresponding to energy En. Okay, so then this En, it is the energy corresponding to the energy I just state psi n. So here there is an expansion coefficient Cn, and we are going to discuss what is the elements of the Cn. Okay, now the first of all, we know that the norm of any wave function must be 1. So if you take the inner product psi with itself, we should get 1. So that means if you integrate the psi star of x and psi of x from 0 to L, so here I am restricting the integration only between 0 to L, because the wave function is 0 uh, before x equal to 0 and after x equal to L. So recall this is a problem of infinite square well. So the particle is completely confined between 0 to L, and there is no wave function outside. So the wave function is non-zero only between 0 to L. So therefore, while integrating, we have to take integration only between 0 to L. So if you integrate this, and you have to do the integration very carefully. So we know that 0 to L psi star of x, psi of x dx is 1. And while integrating, I am going to represent the psi of xt as sum over n Cn psi n e raised to minus I n t by h cross, and this psi star of x xt, I am going to use another index because otherwise this index would be confusing. So since the psi of x I am using the summation index as n, here I am using the summation index as m. So I'm just using another symbol here. So you have to just remember this step. Otherwise, there will be some kind of the loss of information while you are integrating. So you should be careful to give the different notations to represent psi and psi star. Okay. Now, because there are two summations, so you have to distinguish these two summations. Okay. Now the summation and integrations are commutative, so we can take the summation outside. So I have taken the summation outside, and the Cm, the expansion coefficients are not function of position, so it can be taken outside. And even that the phase factor, the dynamical phase factor, that is also independent position, that can also be taken outside. So we have only this integration remaining, integral 0 to L psi m star psi n of x dx, and in the earlier class we have seen that this is nothing but a canonical delta function, because all the energy eigenfunction corresponding to different eigenvalues are orthogonal. So therefore this we have already shown it is equal to delta mn. This delta mn is canonical delta, and the meaning of delta mn, it is 0 when m not equal to n, and it's equal to 1 when m equal to n. So if you use this result, and if you perform this addition, then yeah, what I am going to do is I am going to perform the summation over m first. So I am summing over m, so m can run from 1 to infinity. But if you run from 1 to infinity, so Cn, the n will be a fixed number if you're summing only m. So what happens is when m equal to n, will get a non-zero value, it would be 1, and for all other terms the term would be 0. So therefore this summation would pick up only the one value, that is for m equal to n. All other terms would be 0. So therefore you have to just replace this summation, this entire summation, with a term just simply m equal to n. Then cm star becomes cn star and cn remain as cn, and e raised to mine I e n minus em minus ent by h cross, that would become 1 because em and en would become same. Okay, so the finally what we'll get is, the if you perform this summation over m, the final thing is we'll have sum over n mod cn star, because we'll be getting, after the summation we'll be getting only Cn star and Cn. So Cn star Cn can be simply put as mod Cn square. So this is the one result. So the expansion coefficient, the mod square of expansion coefficient, the sum of mod square of expansion coefficient must be unity if the wave function is normalized. So if the inner product of wave function is 1, then the sum of mod square of all these expansion coefficients must be 1. Okay. Now, it is not a time to interpret the meaning of what sign. So, in order to interpret this, we have to do one more thing. So, what I am going to do is I am going to calculate the expectation value of operator, particularly the Hamilton operator. So we know that the expectation value of Hamiltonian gives the energy, the measured energy of the system. So the expectation value of Hamiltonian. So for any operator in general, the expectation value is the inner product of the operator between these wave functions. So it is psi of xt, h psi of xt, or in Dirac notation we can write, it is bracket notation, it is psi h psi. Now the psi h psi, if you go to this integral form, it is again, this integration is from 0 to L, because we can exclude the integration up to 0 and after and also after L. Okay, so obviously the actual integration should be from minus infinity to plus infinity. But for this problem, there is no need to integrate from minus infinity to plus infinity, because the wave function is not zero, only in between 0 to L. So we have, again I am performing the integration only between 0 to L. So 0 to L psi star of xt h psi of xt dx. Now the next step is I am going to expand both psi star and psi in terms of the energy eigenfunctions, the stationary states. So again I am going to use the different notation while summation. So the psi of xt, I am putting the symbol m, and for psi star of xt I am going to expand with index n. So I am going to use different index, only this m and n, if it interchange, that doesn't matter. So either of the symbols you can use, m, n, or any other symbol if you want to use k, l, anything is possible. There is no restriction of the index. So for my convenience I am going to use m and n. Okay, so now in this case many terms we can take outside the integration. Again, the summation n can be taken outside, the expansion coefficient cn star cm, and the dynamical phase that can also be taken outside. And we have 0 to L psi n star, and when h acting on the psi m of x, when h acting on psi m of x, remember this all the psi n's are the energy eigenfunctions. So h acting on psi m of x would give the energy em and psi m of x, because psi m of x is the energy eigenfunctions. Okay, so if h acting on psi m of x, it leads to em psi m of x. So this integration will limit into this. All other terms I have taken outside. Now again, in this integration, this em is not a function of position, it can also be taken outside. And if that is taken outside, then the remaining thing is only 0 to L psi n star x psi m of x dx, and that is nothing but the canonical delta mn. So I can just replace this integration with a canonical delta mn, and em is outside. Now we have to sum it over. So I am going to perform the sum with summation with m index first. So I am going to run m from 1 to infinity, and I will try to add all the terms. And while adding all the terms, only one term would be non-zero, because this delta mn, when m become m takes the value n, then only that term is non-zero. Or for all other m, it would be zero. So this summation will pick up only one value. that is for m equal to n. So if you put m equal to n, it will become Cn star Cn. Cn star Cn can be written as mod Cn square, and this exponential factor that will become 1 because its power will become 0, so the e raised to 0 will become 1, and instead of em I can put en. So the expectation value of h is sum over n mod Cn square en. Now it is a time to interpret what is mod Cn square. So recall, if you have some distribution of some data, for example, the marks of students in the classroom, how will you find the average? So usually the average value of the marks. So average marks, okay, maybe m marks. I can put simple m. Okay, so different students may be taking the same marks. For example, some students might have scored 100 marks, maybe two students scored 100 marks, and five students scored 90 marks, and some of them scored 70 marks, etc. So there can be number of students scoring the same amount of marks. So then usually what we'll do is we'll find the total marks divided by total students. Let the total students is capital N. Okay, so let N1 is the number of students with M1 mark, and N2 is the number of students with M2 mark plus etc. Then Nk with Mk marks divided by total N. What would be this value? So this value can be written as N1 by capital N times M1, N2 by capital N times M2 plus N3 by capital N plus M3 plus etc. Nk by capital N times Mk. So here N1 by capital N1 by capital N is the number of students scored M1 marks divided by total number of students. So actually that is a chance to get the M1 marks for the students out of N students. Or in other words, it is a probability to get M1 mark to M1 mark to students. And similarly, N2 by capital N would be the probability to get M2 marks, and N3 by N is the probability to get M3 marks, so on. So then this can be written as the probability to get M1 marks into M1, the probability to get M2 marks into M2 plus etc. Or it is sum over K, the probability to get MK marks into MK. So the average marks can be written in this way. Okay. So if you compare these two results, because earlier we have found that the expectation value of Hamiltonian is sum over n mod Cn square En, and in case of the marks of students, actually that is not that much probabilistic event, but if you use the concept of probability, then the average marks of the students scored in the classroom can be written as a sum of product of the probability to get the marks mk times the marks mk. Okay, so if you compare these two, then we can what will be the interpretation of mod Cn square. So the mod Cn square can be interpreted as the probability to get the energy eigenvalue En in a particular measurement. So if we have a quantum mechanical system, the quantum mechanical system, for example, the particle confined in a box, then in general it can be in some arbitrary state, and it can be a superposition of the various energy eigenstate. And if you are trying to find its expectation value of energy experimentally, what we'll do is we have to perform the number of measurements, and we'll get the expectation value. Then in each measurement you will be getting certain value, and it is a probabilistic result. So for in each measurement you will be getting some value. So suppose in first measurement you might have got the energy as E2, and some other measurement you have got the energy as E5, in some measurement you have got the energy as E1. So if you perform a very large number of experiments, then we can find that its expectation value that is almost a constant, and expectation value would be the sum of the product of the probability to get one energizing value and the corresponding energizing value. Okay, so this we have discussed earlier also in some aspect. So the experimentally what we'll do is if you want to perform the energy of a particle in a box, then there should be the ensemble of systems, many systems, ensemble of the same system, and if you perform the energy measurement, I'll be getting different values. So, but this can be E2, this can be, I found it is in E3, this can be again in E2, this can be E4. So the various copies might be giving different results. So the average value of energy, it is the sum of the probability to get the energy eigenvalue En and En. This is the final result. Okay, and theoretically, we are finding that the expectation value of Hamiltonian is sum over n mod Cn square En. So this mod Cn square is nothing but the probability to get the energy value En. Or in other words, the energy eigenvalue En is related with the energy eigenfunction. So recall our psi of xt is sum over n c n sin of x e raised to minus e n t by h cross. So then this expansion coefficient cn is nothing. The mod cn square gives a probability to find the state of the system into the sin of x, because this is a superposition of various energy in state psi 1, psi 2, etc. Then, while measuring the system, it will collapse to one of the energizing state. It may collapse to psi 1 state, or it may collapse to psi 5 state, or it may collapse to psi 3 state, etc. Okay. Now, what is the probability to collapse to one of the state? So, probability to collapse to one of the state is given by mod Cn square, or mod Cn square is the probability to find the system in the energy state. Okay, I will repeat what I have said. Now, in order to calculate the expectation value experimentally, uh, we should have the copies of the same system. So if you want to find the expectation value of energy for of a particle confined in a box, uh, we need a very large number of the same system to find the expectation value. So we need an ensemble of systems. So with a single system, we cannot find the expectation value. With a single system, we'll get one definite value of the energy, and the value of that energy will be changing every time. So once you measure the energy and you got E3, in the consequent measurement, you might not be getting E3, you might be getting E5, or you may be getting E6. Okay, so there are two ways of doing it. So one, you can have an ensemble of system with a large number of copies of system and perform experiment in each copy, and you will be getting different result. Now, if you found the energy as E2, so that means the system is collapsed to the state psi 2. And if you got the energy as E3, that means the system collapsed to the state psi 3, and so on. So the probability to get the energy eigenvalue E2, it is mod C2 square, and it is same as the probability to get to the collapse to the wave function psi 2. So either so conceptually it is acting on the collection of Mendel copies of the system, or experimentally you might be performing on single system, because it may not be possible to make uh, thousands of copies of the same system. So what we'll do is we'll perform the measurement on this same system for number of times. So if you perform the measurement to a system to the number of times, to a large number of times, then you can calculate the expectation value, because in each measurement you'll be getting different result, and if you do all the calculations, if you sum it or all the values divided by the total number of experiments, you will get you can get the average value or the expectation value. Okay, so this Cn plays a major role in the calculation of the expectation values, because this mod Cn square of in any kind of expansion that gives the probability to collapse the state into one of the adjacent state, or is the probability to get the corresponding energy agent value. So this is only one example. So here we have taken the example of the energy agent function. Now in the same way, you can expand the system into the other eigen functions as well. For example, in the case of spin system, you can expand the state in terms of the spin eigenstates. So then the probability that expansion coefficient would be the probability to find the system in one particular spin state. For example, consider a spin of particle. So there are two possibilities. It can be spin up and spin down, and the spin operator usually represented by symbol Sz. So the Sz acting on the spin up would give plus h cross by 2 spin up, and Sz acting on spin down would give minus h cross by 2 spin down. Okay. Now suppose the state of the system is represented as root 3 by 2 spin up plus 1 by 2. So instead of I just change the number 3 by 3 by 2 and 1 by, yes, instead of 1 by 2 it should be, okay, I think it works. What is mod c1 square plus mod c2 square? It would be 3 by 4 plus 1 by 4, and that would be 1. Okay, so this is okay. So we can have a root 3 by 2 spin up plus 1 by 2 spin down. So it is the mod c1 square plus mod c2 square is 1. So that means this inner product size psi is normalized, because the inner product between the spin ups are 1, and inner product between spin downs are 1. The inner product between spin up and spin down is 0. Okay, so using that, it is very easy to show that this psi is having the uh, norm, unity norm. So psi is root 3 by 2 spin up plus 1 by 2 spin down. So this means that if you're trying to find the spin of this state, then there are two possibility: either it will collapse to spin up, or it will collapse to spin down. And the probability to get the system into the spin up would be mod square of this quantity, and that would be 3 by 4. And the probability to get the spin down is 1 by 4. So if you perform very large number of experiment, maybe 1 million times, then one quarter of times the spin of the system will collapse to spin down, and three-quarter of the times it will collapse to spin up. So that is what is basically the meaning of this expansion coefficient. So by just, if the state is given in terms of the superposition of different eigenstates, then that easily represent what the probability to collapse that system, collapse that state into that particular eigenstate. Okay. Now the last we'll discuss how we can calculate this Cn if a wave function is given. So how to find Cn? So this is one simple problem. So in general, the finding of Cn is from the initial condition. So the step is, if you have an unknown problem, first of all we can use the time independence from the equations. So the first step is use the time independence from the equation and find out the energy eigenfunctions psi n. And once you find psi n, then it is possible to expand a general state psi of xt in terms of this psi n is of this form. And there comes Cn, and the meaning of Cn we have already found. It is a probability to find the system in the eigenstate psi n or in the energy eigenvalue En. And now how to find this Cn? So the Cn can be found using this condition. So if the initial value of wave function is given, the psi of x0, then we can calculate Cn by performing this integration. So just integrate psi n star psi of x0 dx. So if you integrate this, you will get Cn. So this integration actually exploiting the orthogonality condition, or more correctly, the orthonormality of energy eigenfunction. Well, okay. So we can have a simple example of this. So consider a particle which is in the infinite square well. So infinite square well we have already discussed. So the step number one we can bypass because we already found what is psi n. So that is why I have taken the example of the infinite square well. So consider a particle is in the infinite square well and has the initial wave function psi of x0 as a into x into L minus x between 0 to x less than n, and obviously the wave function must be 0 otherwise. Okay, now how we can find the psi of xt, or how we can find Cn. So once you find Cn, we can find psi of xt. So psi of x in general can be expanded as sum over n Cn, psi n of x e raised to minus I e t by h cross. And psi n of x we already know because for the infinite square well, the psi n of x can be written as root 2 by L sin n by x by L, where n can take values 1, 2, 3, etc. And the corresponding energy eigenvalue En or n, sorry, energy eigenvalues are n square pi square h bar square divided by 2 ml square. Okay, because this L is the width of this one dimension well, so that comes in the denominator. Now we can find the Cn, the expansion coefficient Cn, using this integration. So integral psi n star psi of x0 dx. Now while this integration we have to perform only between 0 to L because the wave function is 0 otherwise. Okay, now before performing this integration, first we have to find the constant a here. So there is in the initial psi of x0, a constant a is given and which is unknown to us. So first of all, we have to calculate this a in terms of system parameter. For that, we can use the normalization condition because the norm of the wave function must be 1 always. So it must be 1 even at time t equal to 0. So the integral or the norm psi of x0, psi of x0 must be 1. So that can be written as integral 0 to L mod psi of x0 square dx equal to 1. And just integrate by substituting psi of x0 is a square x minus L minus x square dx. And if you perform that integration, you'll get a is equal to the root 30 by L raised to 5. And once you find that a, then just substitute the psi of x0 in the expression of Cn that we have shown earlier. So this is your Cn. So Cn is integral 0 to L psi n star of x. So since this wave function is real wave function, there is no complex conjugate present here. So the psi n would be root 2 by L sin n by x by L, and psi f of x0 is this, and just integrate it, and we will be having two integration, and these two integration. So because we have x into L and x square, We can take many things outside. So root 2 by L can be taken outside integration. Root 30 by L raised to 5 can also be taken outside integration. So root 60 by L raised to 6 will come outside. And we have two integrations. So this integration can be used, can be found by using the product rule of integration. And if you do it very carefully, you will get the result. So you can just refer the textbook if you want the further steps. So I will just get starting my discussion. So the Cn I will get finally 0 when n is even, and the waveform this Cn will become 8 root 5 root 15 by n by q when n is odd. So if you substitute the Cn, then we'll get the total wave function. The psi of xt is of this form. Okay, so that's all about the final solution. So I will just summarize what we have discussed so far. So what we have done is we tried to find the meaning of the Cn, the relevance of the expansion coefficient Cn. So in case of any expansion, if you in case of any expansion of wave function, the Cn gives the probability to find the state of the system, or to the probability to find to collapse the state of the system to one of the eigenstate. So the mod Cn square is the probability to collapse the state into the state psi n, or it is the probability to get the energy eigenvalue En. And the sum of all probabilities, all those probabilities must be 1. So that is what we have seen here. The sum over n mod Cn square equal to 1. So if we have the many possible eigenstate psi 1, psi 2, psi 3 up to psi 10, then if only 10 states are possible, then if you sum the probability or corresponding to all state, it must be 1. So that is what is written here. Mod sum over mod Cn square must be 1. And after that, we have discussed how we can calculate the Cn for a particular problem. So the general procedure is this: first you to find the energy eigenstate by solving the time independence from the equation, then express the wave function of this form: psi of x as sum over n Cn sin of x e raised to minus E n t by h cross. And by knowing the initial condition, that is psi of x0, we can find Cn. So this is one of the simple way. So for this, we have to know the initial state. Okay, so otherwise the procedure would be different. So if the initial state is known, then this is a procedure, and we have shown one simple illustration. Now I just want to show this illustration in Geogebra, how the wave function changes with respect to time for this particular case. Okay, so this is a wave function which is already given to us. This v of this the wave function. So wave function is root 30 by L raised to 5 x into L minus x. So this is my wave function for now. So this is a wave function. Okay. Now this length, again length we can change if you want. So let us put length as 2. Now this is the initial wave function. Now we can, if you try to find the total solution is I have represented in the form of s of x, and s of x can be having a summation, so many multiple summations are there. So if you consider only the first term, the wave function would be look like this, but there is many summation. If you just recall what is psi of xt, this so this is a form of the wave function. So there are many terms present here, sum over n equal to 1, 3, 5, etc. So if you considering only the first term, then obviously you will not be getting the exact solution at time t equal to 0. So remember, record here time t I put as 0. So just delete. So the time is 0. Now if you add one more term, then by adding the number of terms, it will become the more correct. It will exactly matches with the wave function at psi of x0. Now this is at time t equal to 0. Now so that means this term is 1 now. This term is 1. Now even time increases, what would happen? So when time increases, obviously the wave function, the shape of the wave function must change. So I just want to switch on the time here. The time I'm going to run. So the time I am running now. So that purple color represent the wave function at psi of x0, and this orange color is the oscillation of wave function on increasing time. Okay, so it is moving very fastly. So we can decrease the speed as well. So now if you decrease the speed, then you can see what happens. So this will be the variation of wave function. So I am taking only the up to 3 terms. If you add number of terms, you'll get more accurate result. So up to 5 terms I can add, and you can see that while changing the wave function, sometimes it matches with the exact wave function and changes again. So this is the change of wave function. That is why it is varying from positive value to negative value. But if you plot the modes square, then obviously it should be having only positive values. Okay, so that's all for the time being. So we have discussed the relevance of Cn and how we can calculate Cn for a particular problem, and we have illustrated in case of particle in a box. And the same thing I have shown you using GeoGebra, how will be the time evolution of the wave function with respect to time if the initial wave function initial state is fixed. Okay, so that's all for the time being, and in the next class we'll start with the new problem. It's called harmonic oscillator. So thanks for watching this video. See you soon.